recording, and we see you.
So thank you, everyone. So the slideshow is good now, or you see the speaker view?
We can hear you. Just let me.
I would like to make sure like you are seeing the slideshow view, not the speaker mode. So you see my full screen or the.
Yes, I see. I see your screen, and we can hear you well.
Thank you. Good afternoon, everyone, and thank you again for kind of giving this opportunity to present some of my research and some kind of basic information. And I already I was listening lots of presentation, very good presentation, and lots of experience. The peer expert that already shared. So I will quickly share some aspect, especially the greenhouse energy requirement and the optimization. As like I very recently joined at UC Davis, January 2021, about 11 months now. So in this presentation, I will cover some of the research from UC Davis and most of the research so far I did the outside of the UC Davis. But it will be kind of very general, so I'll appreciate like if you have any question, definitely we can answer that things. So today, for this presentation, I will mostly go over like kind of prospect and challenge, very basic background, and mostly I will talk about the energy. So what is the energy challenge and how what is there like kind of in a number, like how big that challenge, and then we'll talk about like the energy efficient, greenhouse safe, and orientation design, and finally a little bit on optimization of the greenhouse envelope for reducing the energy cost. So we know it's very kind of well established that we need the control environment agriculture, and I would like to add some kind of background on that things. Our traditional agricultural practice, we have kind of trilemma problem. Trilemma means we need like a huge number of increase for food because we are based on our prediction that we need to produce about 70% of more food for providing the food security for the increased population, as well as the people are moving from the rural area to the urban area. So that means we have shortage of food. At the same time, our agricultural contributes significant amount for environmental degradation. And because of using huge in natural resources for agricultural production, we are kind of decreasing our natural resources. So that's why like it's called the trilemma problem. So in that aspect, definitely the control environment agriculture has significant benefit in terms of the land use, in terms of like most importantly, the water use, as well as to reduce the food mileage by producing food in local region instead of importing the food from long distance. And the food mileage is also concerned because like if you see the greenhouse gas contribution from the agricultural sector or the food production sector, the transportation is a significant number. Almost 11% could be contributed because of the food transportation from the long distance. And this is kind of the overview of the industry in terms of control environment ag over the world. And this is also kind of showing a kind of prediction of the control environment ag or the indoor farming, like the projection compared to the indoor farming. And we can see the expansion of the control environment ag is significantly higher than our traditional agricultural system. And this is the vertical farming also is a part of control environment ag, but it's like without supplemental lighting. So in that aspect, we can see that compared to 2013, the number we can expect in 2023, according to the BBC, is almost like 6.4 billion, whereas it was only $4 billion industry in 2013. Okay, so now we already talked lots of different benefit and why we need control environment ag and expansion of the industry. But we have some challenges. Some research, some of you already mentioned there are big challenges in control environment ag. So this is one of the report I just found from one of the group. It's called the Control Environment Agriculture Census Report. So they collected this data from 300 commercially grower in different countries, and this is kind of showing that for different types of the controlled environment ag facilities, how they are making money. So we can see almost like irrespective of all different types of the facilities, greenhouse, rooftop, indoor farming, shipping container, or the high tunnel. So most of them, like about 50% of them, they just said that they're making money, but about 50% they're saying either they're losing money or like in the break-even point, or like they don't have kind of exact data. So that is a significant issue, like almost like 50%, they have some sort of concern in their production, either for making business. This is another report for the USA. It's from 2013, and I think they have already another updated report. But based on the US report, you can see also the same situation except for the flower production. So you can see like shipping container, indoor vertical farming, or the greenhouse, all have the like a significant number of the people, they're not making money. And if you see the indoor vertical farming, almost 73%, they're saying that they're not making profit. And I was also surprised like by one things, like for the low tech plastic greenhouse, this is like not that much a very high tech, but it's still like they're saying 75%, they're saying they're not making money. The reason could be like this low tech greenhouse, the yield or the production is significantly lower compared to the other facilities, but they have some kind of the capital cost. And now, like this graph is kind of showing the actual trend of the controlled environment ag in USA, like 57% are leafy greens, 16% tomato, and the others microgreens. So as I mentioned, like in terms of the types of the crop, we can see the flower production case. Most of the people, they're saying that they're 100%, they're saying they're making profit. But in all other case, like herbs, microgreens, a good number of people like saying they're not making money. That means we have some big challenges. So I just try to kind of summarize these challenges. Like the most important issue is the capital investment and the higher energy demand. And also this technology is kind of not brand new, like long time. There have different studies and development, but still there have some kind of limited technological support for this controlled environment ag. So we definitely know like we can grow any types of the plant in controlled environment ag, but from economical point of view, we cannot grow all different things so far based on the current the economical market. So that means the limited types of the plants we can grow. Sometimes also some people, they have kind of wrong perception in terms of the nutritional quality. Either they will prefer the open field crop or the crops that's growing artificially, growing under the artificial lighting system. And also like there have lots of people, they're doing business, but they need some kind of good economical business model to have some kind of the knowledge so that how much they can make profit based on the system they're designing or they're operating. So in that aspect, like if we see like the major cost is the capital, the labor, and as well as like the environmental or the pest control things. So this is now I will show some kind of data from one of my research. So as I did my PhD in Saskatchewan, in Canada, that is kind of very cold region, like in the north, and we just try to see that like what is the operational cost in a commercial greenhouse facilities in Saskatchewan. So you can see that the energy cost is a significant, like about 23% for including the lighting and the heating, and 2% for the CO2. And the labor is also definitely the largest component of the operational cost in North America. And I think Professor Liu already showed that one things for the indoor vertical farming case, like the high energy cost. So I also try to collect that same data from one of the professor like Kojai, and it's showing that for indoor vertical farming, the electricity is the major component of the energy cost. And if we just break down that things out of this 28% of electricity, we can see that for plant growing under artificial lighting, like almost 70% of this energy is used for the lighting purpose. And this is one of the study I just recently read that article, and they were trying to kind of study the three different types of the control environment act, like the low-tech greenhouse without any supplemental lighting, and also high-tech greenhouse, and as well as the plant factories for three different locations like UAE, Netherlands, and Sweden. And they were trying to see like the different component of the energy used for three different facilities in three different locations, and they are trying to present the data in terms of the megajoule per square meter as well as the megajoule per kg of the production. So you can see the plant factory, they basically don't need any kind of heating because the supplemental lighting can provide, if they need any kind of the heating, that should be kind of enough. But for plant factory, the most of the energy required either for cooling, dehumidification, as well as the cooling of the LED. And in UAE, they basically even for the greenhouse, they don't need any kind of energy for heating. Mostly they need the cooling and the dehumidification. So now, like based on that things, we can see like the energy is one of the biggest concern for these control environment agriculture facilities. And from that aspect, like my lab, like at UC Davis, we mostly focus how we can reduce the energy requirement for these control environment facilities, as well as like how we can kind of make this system more sustainable. So in that aspect, so my lab is focused on the three different aspects of the sustainability. And this is it's called the triple bottom line, the planet, profit, and people. So based on that concept, my major goal is how we can achieve the net zero energy status for control environment agricultural facilities. So if you don't have idea about the net zero, like it's basically based on the annual basis calculation. So how much energy you are required for these facilities, and if we can produce same amount of energy from on-site, or like if you get the renewable energy from other sources, if that is in a balance, then you can kind of claim that your facility is net zero. And this facility is very popular for building, like commercial and residential building. And just after finishing my PhD, like I work in HVAC industry, as well as like as a postdoc, I work on commercial and residential building. And they're kind of very advanced to achieve the net zero energy status. I think on that aspect, like as control environment agriculture, facilities are becoming more energy intensive. And in that aspect, this will be the biggest challenge to achieve the net zero energy status. And if we can achieve that things, we can get close to the sustainability of this production system. So how can we achieve the net zero energy status? The most important things, we have to improve the energy efficiency. So in that aspect, like we have to design the efficient building envelope. We have to choose the construction materials that those are more efficient to minimize the energy transfer. As well as we have to focus on the renewable energy use, like either it could be on-site or off-site. Could be focus on the solar, wind, as well as other sources. At the same time, another important aspect could be the focus on the circular economy. That means like how we can efficiently use the waste resources from these control environment facilities for producing the fertilizer as well as like the energy production. So in that case, this could be one of the concept, like if we can harvest the rainwater, as well as if we can use the biomass from the production facilities for organic waste production, as well as for the biogas production, and that could be used to the facilities, and thereby we can reduce the impact of this production facility. Now I will talk a little bit about the research that so far I have done. And in that aspect, like I just classified my research in two different aspects based on my previous experience. Like for my PhD, I focus on two different types of the greenhouse, the conventional greenhouse, as well as the Chinese style solar greenhouse. For my PhD, I worked on thermal environment models. So I developed two different types of the energy simulation model for conventional greenhouse as well as the Chinese style greenhouse. So based on that developed model, I did some optimization as well as some energy analysis. I will just quickly present that. So this is one of my result from my PhD. We tried to did some analysis. What could be the efficient shape and orientation? There are large number of study already for different location. Uh, and most of this study, like there is the conclusion is that this shape and orientation could be significantly different in different location. So in that aspect, like in Saskatchewan, Canada, we try to kind of do that optimization because there was no studies open in Canada in terms of the shape and orientation. And we focus on the greenhouse shape and the orientation, north, south, and east, west, and also the angle and the span. For the shape analysis, like this result is basically showing like we choose 5 different shape that is commercially kind of practiced control environment ag. And the first one is kind of showing the solar gain in 5 different shape. And we can see that the uneven span shape is the maximum solar gain in cold region in Saskatchewan. What we can see in terms of the annual heating requirement, so in that aspect, we can see that uneven span greenhouse is not that much significant that we can see from the solar gain. As solar gain giving beneficial, but in terms of the total heating, it's not that beneficial. The reason is that this is very extremely cold region, and if we have long surface exposed to the outside, in that aspect, the solar gain definitely will be higher. At the same time, the heat loss from the indoor will be also higher. That's why like this difference is not that much significant. Now, in terms of the orientation, we also try to focus on 2 different types of the greenhouse, like the single span and the multi-span greenhouse. And we can see for the single span greenhouse, the east-west orientation is definitely beneficial for heating and the cooling both aspect. But there was not that much information on what will happen like if the greenhouse is multi-span. So if we can see that if the greenhouse is multi-span, so in that aspect, the heating significance, the benefit from the heating aspect is not that much significant as like single span greenhouse. The reason again, it's kind of like for the multi-span greenhouse, like the length with ratio is less, and that aspect you have kind of the less benefit in terms of the heat transfer. Then we try to see that what will be the impact if we just increase the span, like from 8 meter to 16 meter for single span and multi-span. And we can see for the single span, if we increase the span width, we can get the like kind of definitely the less solar radiation, because if we increase the span, the surface area exposed to the outside will be less. But the totally opposite result for the heating requirement. So you can see for the single span, if we increase the span, that aspect, we can minimize the surface area exposed to the outside, and that way we can minimize the total heating requirement. So that means like if we can increase the from a span from 8 meters to the 16 meters, solar gain could be like 30 to 35% higher. But at the same time, like the heating requirement, we can decrease like of 15% if we increase the span width from 8 meters to 16. Then very recently, so I had an undergraduate group at UCDAP, so I just tried to kind of expand that research from my PhD. So we just added one different shape, like the Chinese style shape, and we did some analysis, 3 different locations in California. So what could be the difference, like if we do that analysis? So we choose 3 different locations, like the Bridgeport, Santa Rosa, as well as Imperial. And Bridgeport is a little bit cold, and Santa Rosa is kind of mild, and the Imperial is kind of the hot region. So in that aspect, like this in the Bridgeport, you can see the majority of the heating energy is required for the cooling, and a significant portion of the energy is required for the heat. And we can see like in that case, like for the Quincy, is kind of the lowest energy required, and For Santa Rosa, we can see it's a little bit warm, and so in that aspect, we can see the cooling cost increase significantly, but the heating cost also kind of decrease because this is a relatively warm climate. And Imperial, we can see the mostly required for the cooling and very small amount of energy is required for the heating. Then we also try to see the impact of the orientation. So we try to change the orientation from 0° south surface to up to 90° with 15° intervals in terms of the orientation. This is the result from 0° south surface to 90°. So you can see for all three different locations, in case of California, like there is not that much kind of significant to the solar gain. So there have some change, but it's not the big difference. The same things for the total energy requirement. So we can say like it's kind of very small significant for the orientation. Now I will talk a little bit about the optimization work that I did for my PhD. So in that case, like I will show the result for the Chinese style solar greenhouse. So in that aspect, like Chinese style solar greenhouse, they have kind of minimum transparent surface, and they have some component that is close to the building. So in that case, we just choose the different parameters like the construction parameters, crop related parameters, as well as the indoor environmental control parameters. For this analysis, we consider a 600 meter square east-west orientation greenhouse in Saskatchewan. And we just use the local sensitivity analysis approach, and we just the parameters that we use for quantification with the sensitivity coefficient. So now I'm just showing only kind of very selected result because of the time limitation. So in that case, I'm just showing is the thermal blanket, what is the impact, and the glazing as well as the perimeter insulation. So you can see like for the thermal blanket, if we increase the conductivity, so the heating cost is significantly increased. And the same things also you can see for the cover and also the perimeter. So in terms of the building construction for Chinese style solar greenhouse, these are the three critical parameters that have to be kind of efficiently designed for the poultry zone like the Saskatchewan. These are kind of finish out my presentation, and I will appreciate like if you have any question, like we have some time. Thank you.
Thank you, Dr. Ahmed. If you can, start sharing your screen and